The last speaker in this morning before lunch session is Felix Schwenninger from. Are you still in both universities, actually?
Yes. Yes.
Ah, okay. I was not aware of that. Okay,
but so I'm currently in Vienna, so.
Okay, this is okay, closer to me actually. So. So from Twente, Hamburg / Vienna, and we probably are not going to talk about networks this time. So we will hear about Baillon's theorem on maximal regularity. So thank you, Felix.
Thank you, Marietta, and thanks also to Jochen who asked me to come here. And I would have really loved to come to Russia, I have to say, but yeah, these circumstances are difficult. I'm very happy to have heard a few very nice talks so far. Unfortunately, I have another conference this week. That's why I'm not so present as I would like to be. In any case, I would like to show you some recent results I've been working on with Birgit Jakob and Jens Wittermeier from Wuppertal. And this is something that is related to maximal regularity, but I should already say here that this is with respect to some kind of exotic maximal regularity. So I will explain why this comes in, and this is also the content of Baillon's theorem, which I will also show you in a second. To have a gentle, oh, this is not working here. Yeah. Okay, my clicker does not work, then I do this with the mouse. To start with a gentle introduction to maximal regularity, I have this slide here, and I should also apologize to, I think, 2-3 people in the audience that may have seen parts of this talk already. So I'm sorry that some of this is something you probably have seen and you hopefully know. But I start here with a gentle reminder of what maximal regularity actually is, and this is a classical question that keeps on reappearing in PDEs, in fact. And I will write it here in this abstract form. So you have an equation x dot equals to ax plus f, so this inhomogeneity f is the one that drives the regularity. So the question is whether other terms in this equation other than f do have the same regularity than f. And to be more precise here, one case could be, and this is the most classical one probably, if f is assumed to be an L2 function in time, so time with is here the variable t, and you map into an abstract space x that will always be assumed to be a Banach space. Whether this regularity of f in time carries over to x dot and ax, so to the other terms in the equation. And of course, as soon as it carries over to one of those by the equation, it holds for the third term as well. So this is enough, of course, to simply consider ax here. And as I said, I mean, this is a classical notion in PDEs, but we will look at this here from a purely operator theoretic viewpoint. So I won't talk about applications of that. I may touch this at the very end of the talk, why the things we do here are not so exotic in the end. But let's make this a bit more formal and define the setting of this talk. And the setting is always that A generates a C0 semigroup. I did not write this here. So all semigroups I'm going to consider are strongly continuous, denoted by TT, on a Banach space X. And the letter C is in the following a placeholder for LP, or the continuous functions. And this will be clear in a second what this means here. So then we say that A has maximal regularity, or MR, with respect to C, if the following function has the property that it is in the space C of 0 tau x, if F was in 0 tau x. So in the view of the previous slide, you could for the moment replace C by L2, and then what you have here as a function is basically the function that is AX from the previous slide, because this convolution of the semigroup with the function f is nothing else than, at least formally, the solution to the differential equation, the linear differential equation. Okay, and as I said before, here, if you only consider AX for this question, this is enough. You don't have to consider the derivative x dot. So this is the notion, and this is a well-studied notion. And let's have a few more comments about literature and history. A very simple observation is if A is a bounded operator, and I denote this here by this calligraphic L of x, then it always follows that A has this property. And then it doesn't even matter which choice of C we have here. Right? This is very easy to see, in fact. Now, what is more interesting, but also not very hard to show, is that this maximal regularity property can only appear if the semigroup is in fact analytic. And this makes sense if you recall that maximal regularity is something you usually consider for parabolic problems. So this is somehow justification of that. And this result is old. So these things have been considered from the 60s on. I mentioned a few literature references here. This is not all one could give here, but this is a rather simple consequence of this property that you have an analytic semigroup. Now, what should be noted here is that actually the reflexive range of P's is not that interesting, because this property LP maximal regularity is equivalent to L2 maximal regularity. And this basically says that this L2 case is not only interesting because it appears in applications, but also that this LP setting is not that different from the L2 case. Of course, note here that the non-reflexive cases, 1 and infinity, are excluded here. And those are actually the ones that we're going to look at in a second. What is nice, that is also well known, is that on Hilbert spaces, if X is a Hilbert space, this notion is actually completely characterized by the fact that T is an analytic semigroup. So then you have this property automatically whenever you know that your semigroup is analytic. However, this does not carry over to the general Banach space case. And in fact, and this is now one item for a theory that has, that is very fascinating, I would say, that has developed, say, from the late 80s, 90s, and still 2000s, about what happens if you have a Banach space here that is not a Hilbert space. How could you then characterize this property of L2 maximal regularity? And there's a lot of notions, a lot of theory that has been introduced for that. And okay, I mentioned a few names. Lutz Weiss is maybe one of the most prominent names here, because this related then to the so-called notion of R-boundedness and R-sectoriality, which turned out to be the right concept to study these things in non-Hilbert spaces. Unfortunately, okay, I will not talk about this in this talk, so I will leave it with that at the moment, but I should say that this is something really, I mean, on its own right, very interesting subject. Okay, so usually what I have here, and I skipped this slide, I say this is a visit to the zoo, because now we're going to study some exotic cases. And the exotic case refers here to the fact that this C, this space, is now the continuous functions, or it could be L infinity or L1. Let's keep it for the moment with C. Then a question by Pesi, which is also already quite old, this question, was whether this property in fact always implies that A is a bounded operator. And as you have seen on the previous slide, well, the other direction is trivial, rather trivial. And there are good reasons to believe why this implication should be true. And actually, whenever you start to try to find a counterexample on your favorite Hilbert space, you're doomed to fail. And as we'll see in a second, this is really clear why this is doomed to fail. However, there was an example right after Pesi has asked this question on the space C0, and probably one of the simple semigroups you can consider on this space, namely the diagonal semigroup. And I mean here, this is the semigroup that is diagonal with respect to the canonical basis, and it has eigenvalues -n along the diagonal. And this example, in fact, provides a counterexample to the question. So what can be seen rather directly, as an exercise, is that A has this maximal regularity property with respect to the continuous function. It also has it with respect to L infinity. Well, this is not so important for the question, actually. But it's obviously not a bounded operator, this operator A. So this provides a counterexample to Pesi's questions, and you could say this closes this topic. Well, as always, I mean, there's a yes and a but, or there's a no and a but. And the but comes now here. So this is the next slide, namely by, I would say, classical result and famous result by Baillon from the 80s that states the following. If A has this maximal regularity with respect to the continuous functions, or you could alternatively assume this with L infinity, this actually implies that either A is a bounded operator, or the space X on which A acts is an ugly space. Now, what means ugly here? The reason is that the line would break if I write down the definition. The definition is easy. Ugly means that X contains an isomorphic copy of C0. And this is nice, because this shows that somehow the example by Kato is actually somehow the limit case. So it shows that, okay, this is an example on C0. So there are not so many other examples. Well, there are a few other, but not so many other that you can consider to find a counterexample. Okay, to recall that, I mean, what could be ugly here is, of course, C0, as we have seen, CK or L infinity, but this, of course, excludes reflexive spaces X or L1, for example. Now I take away the question that some could ask here, well, what happens if you assume here L1 maximal regularity, then everything gets dualized and basically ugly becomes containing an isomorphic copy of little L1. And well, the statement holds in a similar fashion. The proof is very similar to that one. Yes, references here. Baillon is the one that proved this first. There's an alternative proof, or much more accessible proof by Ebert Greiner from '92. I can recommend that paper very much, I have to say. The case of L infinity and also L1 was actually treated by Guerre de la Bière in '95. And there's another result that relates to this by Travis. We will touch this in 2 slides, I think. He was studying basically the question whether weak solutions of the Absher-Cauchy problems are strong solutions, and then came somehow to these results. Yes, so a closer look at this theorem, because we're going to need this later on. This is simply, again, the same statement, but now a bit more explicit. So if we assume that A has maximal regularity with respect to the continuous functions, and assume that A was not bounded, well, following the theorem from the previous slide, this should then give us that there exists a copy of C0. Now, this is here more explicit. There exists a sequence Zn that spans a space, so the closure of the span is isomorphic to C0, and it's actually a basic sequence. This means the second item here, that Cn is a Schauder basis of this closure Z. Well, it's normalized in a sense. This is the item 3, so that the norms are not exploding or going to 0 of this sequence. And the last item, this is something that usually is not formulated when Baillon's theorem is written down, because this is part of the proof, namely that if you apply the resolvent operator to the sequence Zn and you let n run to infinity, this goes to 0. So this is a property we're gonna use later on. That's why I stated here. I'm not really saying something about how to prove this, but to give you a glimpse, well, actually the underlying fact that stands behind this proof is a classical theorem by Besaga-Pelczynski that tells you that you may find a copy of C0 as soon as you manage to find a sequence Xn in your space with the following properties. And then the second property here in this line shows already why this is close to having somehow a supremum norm. So you have a sequence and you take any subsequence of it and you sum over this subsequence, and this should remain bounded by a universal constant M. Right, so this is how this is proved. That's a very nice, and the question of course remains here, how to choose the Xn depending on the semigroup or the semigroup generator A. Well, this is what you have to do. Okay, so let's come to the main part of this talk, or the main result, and that's a variant of maximal regularity with respect to the continuous functions. And in order to introduce this variant, let me reformulate the definition of C maximal regularity. And this is something that can be traced back to Travis from '81. It's not explicitly stated there, but it's included in some of the proofs. So Travis says that this property is equivalent to the following property. So you define, or you look at the operator phi tau. This is the operator that maps F's to A applied to this convolution, but the convolution now evaluated at a fixed time tau. And if this is a bounded operator from the continuous functions from 0 tau with values in x to x, then this is equivalent to saying that A has C maximal regularity. So this looks similar to the definition of C maximal regularity, but it's not exactly the same, because if you recall that maximal regularity was saying that a function in T was living in the same space, namely the continuous functions, and this is now an operator that maps the continuous functions to a fixed element in X. Of course, what is hidden here is that this mapping is well defined. So this is part of this assertion in 2. Because obviously this convolution of the semigroup with F need not be in the domain of A. So it's not at all clear a priori why this is well defined, this guy. Now this is implicitly assumed here. If you want to make this more formal, you would probably first of all define an exploration space of the semigroup, extend the operator A to it, and then at least this is formally defined on X minus 1. And then you assume basically that this element even lies in X. By closed graph, actually, this is equivalent to say that this is a bounded operator. Okay, now what we're going to do, and that's the definition you will see in the next slide, I want to replace the space of continuous functions here by L infinity. And clearly, I mean, this is a stronger assumption than the one given here. And we will investigate to what extent this is strong. Okay, I mentioned this before. Actually, what Travis was interested in is another equivalence in this statement, namely that every mild solution of the abstract Cauchy problem is in fact a classical solution. Well, this is something you hardly ever expect. Turns out that this is equivalent to A having maximal C regularity. Okay, and there's another equivalent condition about certain semi-variation. I will spare you with the details about this because it's not important for the rest of the talk. All right, this is a similar slide than you have seen for the definition of maximal regularity, and I think this should now be rather straightforward with what I said. The setting is again the same as before. Now we give this a name. We say that A is called a Z admissible. There's a reason why this is called admissible, but I will not touch this here. If for every T, and in the previous slide this was a tau, and every F on the space C defined on 0T with values in X, the element X of T that stands there, this is A applied to the convolution of the semigroup with F, is itself an element of X again. And it is enough to require this only for some fixed T and all functions F. Then it holds for any other. This is a standard argument, and the same actually holds true for maximal regularity. Okay, recall in comparison that Z maximal regularity was defined to say that the mapping T goes over to X of T is in this function space C of 0 tau X. And this is a different, or a priori different notion than the one we have seen here. However, from the previous slide, we can already tell that if the letter Z or Z is actually the continuous functions, then this is the same. And this is the consequence of this result by Travis. Yeah, so since I included here the LP spaces in this definition, I would like to comment on this. This says this actually gives us, by the nesting properties of LP spaces, that if you have an LP admissible A, where P is less than Q, then automatically follows that A is LQ admissible. So in other words, the L infinity case is the weakest one, and the L1 case is the strongest one. This is a side remark. If P is less than infinity, then it's rather easy to see that X is automatically a continuous function as a function to X. But yeah, this is not so important. Let's look again at Cato's example. And in terms of this new notion, so this was the example again, that as before, or not as before, but as from the things I said before, it was clear that A is maximal regular with respect to the continuous functions, and by Travis' result, this then means that it's also C admissible because these two notions are then equivalent. However, A is not L infinity admissible. This can be shown again by doing a little exercise actually, and what you do is you look for a good choice of your function F, and that has values in C naught, and is an L infinity function. Basically, you choose it to be some kind of step function with infinitely many steps. And you make sure that this convolution is not in the domain of A, and therefore this definition is violated. Okay, knowing this, we can now compare maximal regularity and admissibility. So by Travis's result, we know that those are the same when we have the continuous functions. On the other hand, by this example I just showed you, the Cato example, L infinity admissibility is not the same as L infinity maximal regularity, because, and that I mentioned in my third slide, this Cato example is in fact also L infinity maximal regular. However, one direction is clear because of the inclusion or the containment of this continuous one implication is clear from the definition. That's the one that L infinity admissibility is something stronger than L infinity maximal regularity. Well, for the reference, the L1 case, this is somehow a dual case, but it's in many ways simpler than the L infinity case. This was actually implicitly treated by Carlton and Portal in 2008, where they showed, without using the notion of admissibility, that these things are again equivalent. Okay, so this is now the main result of this talk, and this says the following. If A is L infinity admissible, then this can only happen if and only if A is a bounded operator. And in that sense, it is a refinement of Baillon's result. because the left-hand side of this equivalence is something stronger than maximal regularity with respect to the continuous functions. So this theorem basically tells us that this case that X contains an isomorphic copy of C naught can be excluded under the stronger assumption. So stronger assumption, stronger statement. And it's somehow surprising that, at least to our knowledge, the proof of this result is not that easy. Before I give you a glimpse on the proof, let me try to convince you why you should believe this result and also why you should not believe this result. So the statement is here in the top line again. And as I said before, the only interesting direction is the implication of L infinity admissibility to A being a bounded operator. The other one is trivial. Now, a reason to believe it is that if you slightly strengthen the hypothesis even more, namely you assume instead that A is LP admissible with P less than infinity, then I claim that the statement is very easy to prove. And I give you the proof here. The proof is as follows. You look or you show that the semigroup is uniformly continuous by simply looking at TTX minus X in norm. In the first identity, rewrite this by introducing an integral and the derivative of the semigroup. Well, you can do this first of all for X in a domain of A, then this is really formally well defined. Then you rewrite this by using the generator and you pull out the generator of the integral and you use the assumption that A was LP admissible. And this assumption actually gives us not only that this integral is well defined as an element in X, but also that there is a norm estimate. This is a closed graph consequence. Now, if you believe me that this inequality holds with some constant, then it's clear that if we let t go to 0, and inside this norm here, this is the constant x function, this will go to 0 because this norm of the constant function will go to 0 if t goes to 0. However, what you use here is that p is not equal to infinity, because then this was not true. So you see here why this argument does not work for the case where p is equal to infinity, because then you would not get a convergence to 0 on the right-hand side. However, for this slightly stronger case, you get it here. Okay, you can now discuss whether this is a plus or a minus, why to believe the result. Anyway, minus here, or a con, why not to believe this, is the fact that C admissibility, as we know, does not imply that A is a bounded operator. And knowing this, well, a canonical idea would be to adapt Cato's example to the case where X is L infinity, little L infinity, choosing the same or the canonical operator A. Of course, everybody doing semigroups knows that this does not work, because A is not a generator of a strong continuous semigroup. And well, I say here the word lots, and this is not the example. Well, this shows us, lots tells us that this cannot happen anytime whenever we consider L infinity as a state space X. And the result here somehow, I would say, is in some sense related to this problem of the fact that lots tells us this, so we cannot get easy counterexamples to disprove the statement. So then I would say that this becomes a plus, actually, why to believe the result. Let me check time. I think I'm getting to an end. So may I ask, Marietta, how much time do you still have left?
I think you have like a couple of minutes.
Okay, then I will give you a glimpse on the proof. I mean, I'm nearly done.
Okay.
Okay. Well, this is a structure of the proof. This is not the proof. This is a structure of the proof. And there are basically 4 steps. The first step is a semigroup step, I would say. And the first step is that you show that this assumption of L infinity admissibility implies something about the domain of A. So it implies that the domain of A can be rewritten in the form on the right-hand side. And for those that know this expression, this is a Favart space on the right-hand side. So you show that the domain of A is equal to the Favart space of the semigroup, or the Favart zero space, if you use a parameter. And this is in some sense interesting because, as we know, this statement is always true if X is a reflexive space. But on the other hand, reflexive spaces are the ones that are just not the ones that give counterexamples in Baillon's theorem. So this gives somehow, in some sense, contradicting situation, which is good because we would like to show that there is no counterexample. This is the first step. The second step is actually independent or not directly related to the L infinity admissibility. The second step is simply using Baillon's theorem, because L infinity admissibility implies in particular that your operator A is C maximal regular. And you assume that if A is not a bounded operator, then you find a suitable subspace C. So this C is now referring to the space I constructed in my statement of Baillon's theorem, which is an isomorphic copy of C0. The third item, and this is maybe the most interesting one, is that you show that the resolvent operator restricted to the subspace C is in fact a G delta embedding. And I wrote down what this means. This means that for any bounded closed subset of the subspace C, the set resolvent applied to K is a G delta set. And I explain in a second why this is an important property. And finally, we conclude from this that actually A is a bounded operator by using a lemma from Burger and Rosenthal. And this is a deep result actually about isomorphisms on Banach spaces. Yes, well, I should say that this step 3 is inspired by an interesting or nice result for Jan van Nerven from 92. It is, I think, only included in his book that says that if you have a semigroup on C0, and you know that this item 1 holds, namely that the Favart space equals the domain of A, then the semigroup must be uniformly continuous already. So this is somehow what inspired this technique here. Now, very briefly, how to show this third item. Now, the third item uses this Bourgoin-Rosenthal lemma, and this lemma says when you have such a G delta embedding. And the condition for that is that you have a mapping from a separable space X hat to Y, which is injective, and moreover has the property that it maps the closed unit disk to a closed set. This is also called a semi-embedding, such a mapping. And such a mapping is a G delta embedding by a result by Burger-Rosenthal. So what you do is now you check these assumptions, and for that you have to actually go to an equivalent norm of the space, not the usual norm you started with, and you can then show this. Okay, and I think time is over, so I will skip you the last detail here. And I will finish with a summary slide, which basically shows an extended version of the theorem I just discussed. And I leave the remarks below for the discussion. I thank you very much for the attention.
Thank you, Felix. Any questions from the audience? I guess everybody is still busy reading your last slide.
This was not my purpose, but it's also fine.
So anybody, I think I hear someone, but let me see if somebody.
I think I maybe have a question.
Okay.
To be honest, I'm not sure whether I have already asked you this someone in the past.
Oh, it could be no problem.
Is there any relation to positivity?
Yes and no. So well, the result is general. So then of course you could have a non-positive semigroup, but if you assume positivity, some things get a bit simpler. So well, this is the end of a long journey, I should say. So we tried to prove this result for quite some time, and we had a few intermediate steps, and some of them involved positivity, but well, the final result does not. For example, you have so what I should say, I think this is the first remark I have here below the theorem. The proof becomes relatively simple, or somehow it avoids these Burger-Rosenthal results if you can assume that the dual semigroup is strongly continuous. And if you employ positivity, there are results that guarantee this, that the dual semigroup is strongly continuous. And in that sense, there are relations like for intermediate results. But if you want to show this generally, I don't think that positivity will appear.
Thank you.
I think you did not ask this before.
Okay, that's great.
Okay. Any more questions?
Well, actually.
Yes. Okay.
But there's a question about your previous answer. You mentioned that there are results which ensure that the dual semigroup is strongly continuous, assuming positivity. Could you point me to any of those results? Because I've never
No,
seen
I have to check. I mean, I have to look. I think. I mean, it's van Even. I'm sure.
Okay.
But I'll provide you with this. So I have this in my notes. And I'm not sure about the exact. It's not the book, I think.
Okay. Thanks.
Okay, I think I have a slight question here on the slide point 4. What does it mean that A is 0 class? No, the last slide.
So sorry.
The last slide, point 4.
That's a good one, because this is, of course, meant there to trigger this question. Yeah, I did not explain it. It's obviously. Okay, I mentioned that this admissibility, where is it, actually relates to considering this operator here, phi tau. So admissibility with respect to the continuous function means that this phi tau is a bounded operator. And 0 class means that the norm of this phi tau goes to 0 as tau goes to 0.
Mm-hmm.
So for every fixed tau, this has a certain value, this norm. And as soon as it exists for one tau, it exists for all of them. But it's not a priori clear, and it's not true in general even, that this phi tau in the operator norm goes to 0 as tau goes to 0. It's a stronger assumption, actually. And in fact, a counterexample to this, where something is not 0 class admissible, is this Kato example. There you don't have this. Mm-hmm. And if you look at this proof here, or this argument for the LP case, if you replace LP admissible by 0 class continuous admissible, you can do the same steps, but you end up here with the norm of, the supremum norm, and the operator norm phi tau, phi t, and this would then go to 0. So if you have 0 class admissibility, the same argument as that one here implies that A is a bounded operator. So that direction is rather trivial.
Mm-hmm. Okay.
I have also a question, if time allows.
Yes, please, Christian.
In the last theorem, you used that D in the second assertion that D of A coincides with the Favart space.
Mm-hmm.
You know that this is always true when the underlying space is reflexive.
Mm-hmm.
Do you somehow need a converse of this, or do you need reflexivity to?
No. I mean, this can be true even if the space is non-reflexive.
That's true. That's true. Okay.
So yeah, it's really the interplay of this C maximal regularity plus this identity that gives you the boundedness.
Okay.
Either of those will not.
Okay. Okay. Thank you.
Thanks for the question.
I have a question if there is time.
Yes, Hiba. I think it's lunch break, so maybe
That's the advantage of being last.
So when you were mentioning the steps in the proof of Baillon's result, I think you mentioned a step about the resolvent, and you said you will use it later on, but I don't think I recall when you used it.
Well, it's hidden here on this slide. So okay, and I did not go through the details here, so I can maybe do this now.
Okay.
So S is a G delta embedding. That's what I said. We show that this the resolvent restricted to C is G delta embedding, and you use this then with another result by Burger and Rosenthal that says basically that any such G delta embedding on a space that is isomorphic to C node, and that's what C actually is bounded from below. Okay. So what we show is that this resolvent operator, at least restricted to C, is bounded below, and that's contradicting this fourth item of Baillon's theorem.
Okay.
So if we go back here, Yes, here. This fourth item says that, okay, these CNs are the elements from Z, actually, from the space. So this is contradicting. So if this holds what stands here, your operator can't be bounded from below.
Yeah.
The result operator. And that's where this is needed.
Okay. Thank you.
Thanks for the question. Good question.
Okay, so I suggest we now thank Felix and
Thank
all
you.
the speakers of